So our next speaker is Amitha from Hewlett-Packard Enterprise, and she will be presenting a talk entitled A Record-Based Pointer to Fabric-Attached Memory. Take it away, Amitha.
Yeah, today I'm presenting a talk on one of the proposals that we are working on for CHIUW, which is enabling a record-based pointers to fabric-attached memory. For today's talk, first I will give a brief context about what is fabric-attached memory, and then I will talk about why we consider CHIUW a programming language for the FAM enablement. I will also briefly cover our previous work on enabling FAM access within CHIUW, and we will see more on our current effort, which is supporting pointers to FAM with one example use case. Then I will conclude with the current status of our effort and the next steps. To give a brief context about what is fabric-attached memory, which is called as FAM, I will not take much time as Harumi has already covered the background for FAM in her presentation. Or I will quickly try to recap on what is fabric-attached memory to set a context for the following slides. So fabric-attached memory is basically a disaggregated memory that is made available to all the compute nodes over a high-speed network interconnect. In FAM system architecture, we will have multiple compute nodes connected to a shared memory pool that is referred to as FAM over a high-speed fabric. And each of these compute nodes run their own instance of the operating system. And the number of compute nodes can scale up to tens of thousands of nodes. And the shared memory here is constructed from the nodes called memory nodes. And these memory nodes are connected to the same fabric, with each of these memory nodes contribute the portion of their locally available memory to the shared memory pool. So this architecture basically allows scaling of both compute and memory resources independent to each other. And such resource disaggregation allows us to create a large shared memory pool, which is referred to as fabric-attached memory. And because FAM is large, it basically allows workloads that typically work with larger data sets, and such applications fits really well in fabric-attached memory. And because all compute nodes are connected to the shared memory pool and can access the fabric-attached memory, it allows for efficient data sharing and the communication between the compute nodes. So that is about FAM at a high level. For more details about FAM, please refer to the links provided in the reference section. So now to quickly summarize why we chose CHIUW language for the FAM support. Basically, our primary intention here is to make FAM available to a variety of workloads, and that is possible through enabling FAM access in multiple programming languages. And because FAM usage is targeted more towards HPC workloads, and CHIUW is also written for HPC, we thought enabling FAM access in CHIUW language is more appropriate. And also, there were other few reasons, like as we know, CHIUW is designed to be scalable, like other parallel programming languages, and is faster, portable, and productive, and is of course is open source. So these were some of the key reasons why we considered CHIUW language for the FAM support. To make FAM available in CHIUW, there were few guiding philosophies we had in our mind. So firstly, we wanted to have very minimal changes in the language in order to support FAM. And we wanted to enable FAM access through the existing language construct so that CHIUW user is not required to learn anything new in order to program for FAM. And the second key goal was to provide abstraction. So we wanted to abstract away all the underlying FAM access details from the user in order to provide the ease of programming. So these were some of the key principles in our effort. So now we will see some of our previous work around the FAM enablement work. So we initially started with enabling CHIUW bindings for FAM. So this is basically to allow calls to the low-level FAM APIs directly from the application. So for FAM access, as Harumi mentioned, we use a library called OpenFAM, which is written in C++. So in order to call these C++ methods from CHIUW, we have developed thin C wrapper on top of this OpenFAM C++ library. And we have also developed a chapel module called OpenFAM. The application has to use this OpenFAM module in order to call these chapel binding APIs. As I mentioned, these binding APIs are low-level FAM calls, which are called directly from the application. They do not provide any kind of abstraction. Then our next effort was to enable FAM access through a language construct and provide abstraction. And for the ease of parallel program, as we know, Chapel provides a nice feature called array distribution, and which is also widely used in Chapel application. So we thought enabling array distribution for FAM is more relevant. And for that, we have created a FAM distribution module that basically allows users to store the array data on FAM, and also provides all the features and functionalities that a typical array distribution provides. Like other array distribution, FAM distribution also provides implicit parallelism through domain partitioning. So which means array operations are internally divided into multiple parallel tasks and are executed on the respective compute nodes based on the domain or the index ownership. So all of these conversion of the user level array operations into OpenFAM calls are all handled within the FAM distribution module, and thus abstracts all the OpenFAM specific details from the user. So all of the FAM data allocation and management is hidden from the user. So these are some of the initial work we have done in order to enable FAM access from Chapel. Now we will move to our current proposal for accessing FAM, which is through the pointer. So basically, we wanted to extend our support for FAM through the language construct beyond FAM array distribution. This is because array distribution alone cannot be applied in certain use cases, like enabling complex data structures for FAM, like linked list or map or trees. In traditional programming, right? So typically, the pointers are widely used to simplify the implementation of such data structures. So hence, we also felt enabling pointers for FAM makes more sense for such applications in Chapel also. So hence, we propose to enable pointers to FAM and allow access to the FAM location through these pointers, and even provide pointer arithmetic capabilities in addition. The aim of our effort is to make FAM access easier for the developer through these pointers and not add any extra overhead to the performance. So with this at a high level, our solution enables creating pointers to point to the pre-existing data on FAM. And this pointer basically includes all the required informations like OpenFAM handle or descriptor, the size or the type of the data that it should point to, and the offset information in order to locate the corresponding data on FAM. And this FAM pointer also includes methods to help convert the pointer access into the FAM data access. So with this way, the FAM pointer acts as a wrapper to the low-level Chapel binding APIs, making the access to FAM simpler for the Chapel developer. Because the idea of FAM pointer is to point to a pre-existing data, we are decoupling the allocation and deallocation of the FAM data items from the FAM PTR definition. So all of these allocation and deallocation of the OpenFAM regions and the data items can be handled through the Chapel binding. So these are the high-level details of our proposed solution. Now we will look at where we are at present on this effort. We have already completed the initial implementation of the FAM pointer, and the FAM pointer is implemented using Chapel's record type. We have developed a module called FAM types, which needs to be used in the program in order to use a FAM pointer in the application. And the implementation currently supports functionalities like creation and deletion of the FAM pointer. And it also supports reading from and writing into the FAM location through FAM pointers. And implementation also includes methods like increment and decrement to allow pointers to point to the next location on FAM, and Additionally, we also support pointer arithmetic operation, that is adding on subtracting integers to and from fam pointers. On the right hand side, we have a simple basic Apple example code on how to use FAM-PTR. And as we can see, FAM-PTR can be created using a new keyword similar to any other chapel record instances. And FAM-PTR initialization basically takes arguments like the type of the data that it should point to, and the OpenFAM descriptor to the FAM data, which is an optional argument. The FAM pointer can also be created from an existing pointer using an assignment statement, like other chapel record instances. And for reading and writing the data on FAM, there are read and write methods that needs to be invoked explicitly. And this program also has example of adding integer to the FAM PTR record to make pointer point to the intended location on FAM. The implementation also allow creating FAM pointer to point to null or nothing on FAM initially by skipping the optional argument, which is FAM descriptor. And we can make pointer point to a valid location on FAM later by calling certain method on the FAM pointer. So with this, we have completed the initial implementation of the FAM pointer, and we are currently in the process of enhancing or improvising the initial implementation. So as part of that, we are now adding support for atomic access to FAM through FAM PTRs. And additionally, we are also exploring different use cases for FAM PTR. And for that, we have plans to implement a few data structures for FAM using FAM pointers. So as a next step, we will continue to enhance this implementation and keep adding more functionalities to it as required. So now let us look at an example use case for FAM PTR. And here I have taken KVS, which is a key value store, as an example. The right-hand diagram shows how the key value pair for FAM resident data can be constructed using FAM pointer. In a traditional framework, when keys are mapped to the value means the actual data. But in case of FAM, when key is mapped to a value, that value is represented using FAM pointer. So that means each key is associated with a FAM PTR, and both together represents the corresponding data on FAM. The access
so,
to
Amitha,
FAM.
We have about 3 minutes left if you want to try and wrap up so we can take questions.
Yes, sure. This is the last slide I have. So each key is associated with a FAM pointer, and both together represents the corresponding data on FAM. The access to the FAM PTR is translated to the FAM data access. Hence, any query or an update to the data through key value or a key FAM PTR pair is internally converted into a FAM data access call. So this is how key value pair for FAM data can be represented using FAM pointer. Similarly, any data structures like linked list, trees, and graphs can also be built using FAM PTRs. So with this, I would like to conclude my talk mentioning that our new proposal of enabling pointers to FAM enables an alternative way for FAM access to our previous work in Chapel. And more importantly, our solution provides the ease of programming with FAM and without adding any performance cost. So that brings to the end of my talk. Thank you.
All right. Thank you, Amitha, for the great talk. We have time for maybe one question. If the audience, anybody has questions, please use the reaction buttons to thank your speaker. If nobody has a question prepped, I'll go ahead and ask one, which is, does the pointer arithmetic that in your interface include any bounds checking features to avoid stepping outside the FAM object, or is that something handled by OpenFAM?
Which is currently handled by OpenFAM. So in our FAM pointer implementation, we are not checking the bounds. So we just keep adding the integers to the offset to point to the corresponding location. So when we call OpenFAM APIs with these offsets, so if it is out of bound, we will get an exception back. So this is how it is being handled currently.
Understood. Thank you.